There's like a lot more people here than when I was staring at this computer just a second ago. Where'd you all come from? All right. Let's do this. All right. Hi, I'm Andrew. I work at a company called Domino Data Lab. We build a platform for data science teams. Our platform, or our stack, is mostly Scala. A lot of object-oriented Scala. Where I touch the code base, there's a bit more functional stuff hidden in there. So I guess before I begin, this is the functional track. So how many of you are familiar with type classes already? How many have written their own type classes? Cool. All right, so like maybe 33% of you have written your own type classes. So I apologize to you. This might be boring. I hope not. But today I'm going to walk through what I feel like is a fairly canonical use case for type classes, go through where you want to use them, where you probably don't want to use them, and where you might have to use them. But before I begin, just wanted to have special thanks to Travis Brown. His blog post, Type Classes and Generic Derivation, provided basically the narrative outline for this talk. And then Rob Norris, who is just a profoundly wonderful like teacher and speaker. And so I hope to give this talk in that vein, in that spirit. And I gave this talk earlier at a Scala meetup where Jakob pointed out a flaw, and hopefully I fixed that. So let's go over the goals here. So this pattern is well known in functional programming, Scala community. Comes from Haskell. Basically is there to address a lot of the complexities around generics and replace things like inheritance. So the main point here is we want to make the compiler do some work for us. So let's let the Scala compiler work for us. Hopefully also you'll gain some confidence in seeing this pattern, how to apply it, where to apply it, and then see some applications that maybe you might not be familiar with type classes. So the canonical use case here is that I'm going to take is serialization or deserialization. And so I'm going to start with some very simple data types here. There's a person, address, account with strings, ints, and doubles wrapping them. And we want to have an API for deserialization. In this case, it's just a simple text format. You could also call this like a parser, but it's a comma-separated value where if we have person Fred and their age, we should be able to deserialize it okay as a person. But we want to have some constraints here. The main constraints are that we should never throw non-fatal exceptions. So things like out-of-memory errors are perfectly fine, but things like a number format exception wouldn't be. We also should never get a runtime failure. So we should basically have a form of error in the form of a value. And then we want to remove as much boilerplate as possible as well. So those are our constraints. So let's try this out with just a naive first go. So we have our deserializer, which is parameterized on some generic A. We use the apply method, which gives us some nice syntactic sugar, and basically string.split and apply these things to those types that we had earlier, account and address. And it's actually a really nice API. We can create for every type we want. We can create a deserializer and apply it to this string. And we get a useful type back, not just any, for example. We get account or address, which is great. But there are three big problems here. We allow non-fatal errors to be thrown. So if we were to try to deserialize something with a trailing comma, we might get a match error, maybe a number format exception. So that doesn't meet our first constraint. We also have to keep track of each row deserializer instance for every type we want. There might be a whole bunch of these. till we get to our serious business deserializer, which is where we really get to the heart of our logic. And then we have to write a lot of boilerplate, and that's also closely related to item number 2. So let's do something a little bit better. Let's take the first problem and apply option to it. So now we simply represent failure as an option type. So it either succeeds if it can or returns none if it doesn't work. And it allows us to return that a failure is a value of none, right? And now it's impossible to make our deserializer crash with a recoverable exception. So if the input's invalid, we return a none. But unfortunately, we still need to keep track of every single deserializer. So one way that a lot of Java-friendly libraries, or ways we've done this in the past, before we had a more powerful compiler like in Scala, we might use reflection. And it's actually really easy to write a reflection thing. This is from Travis. You basically match on what's incoming and then just instantiate as instance of. And it gets rid of all the boilerplate. It's really nice. We can just throw anything at it. But it has a big problem. This is really annoying. We can totally write this line where we deserialize a foo without actually telling how to deserialize that. So we're not getting, and this is going to happen at runtime. We're just going to have a none. We have no idea because at compile time, we didn't know that we didn't have a deserializer for that. And we have a whole bunch of other things around runtime issues. One of the libraries we use at Domino Data Lab for our Mongo stuff is called Salat. And along with Salat, which is a runtime or serialization library, we have a wiki article called Surviving Salat. And I'm sure that many of us have these sorts of articles. But it's an article basically detailing all this weird behavior and what to guard against very defensively in your code. So let's go back to our safer deserializer. Let's try to get back to a compile time approach. So we want to adapt it so we don't have to keep track of everything of each of those deserializers. And we want to change it so that we want to make sure that if we just create some type and then try to deserialize that type without actually creating a deserializer, that fails. And so we can do this by, if we give our companion object of safer deserializer this apply method where we pass in a deserializer, now we can write this fairly nice syntax and compile OK, but not have that compile. That's going to fail. So there's a couple of problems. We can define multiple deserializers for the same type. That can be a problem. Also, because we want a deserializer for a single format. And then we know that we want this. So another problem here is that it's really annoying to pass around these deserializers. So we know we want one deserializer for a specific format. So we really have this one-to-one mapping, some like function from A to a deserializer of A. So what if we had we codified this as a method? So if we did this at runtime, we could check, OK, if there's some instance of account, then we return this account deserializer, and we just keep adding on here. That'd be neat. That's also known as a map. So what if we did have some magic map where we could pass in a mapper where we found the instance of the type A to the deserializer, and then we got it, and then we threw some exception if we couldn't find it. That'd be pretty nice. Also, we'd be able to, if we made this some global mapper, we could add deserializers on the fly for when some other feature maintainer of our code or user of our library needs to add a deserializer. That'd be really nice. We just put it in there, and we can pull it out. So what if we could do that at compile time? That would be really neat, and have the compiler do all of this mapping for us. So this is our safer deserializer. This is the one that returns the option that we have to pass around all of the things. Let's make a few just minor modifications. Let's move those deserializers into the companion object. And then let's sprinkle some implicit keywords in there. So the only difference here, implicit, not implicit. Implicit, not implicit, okay? It's the only difference. And now we get the usage that we want. We get the deserializer like that, and we can't compile when we haven't defined a serializer or a deserializer. And we get it at compile time. And now we've discovered type classes. So what are type classes? There's like a lot of like writings about type classes. This is my distillation of it. It allows us to associate operations with types without modifying the definition of those types. Scala implements type classes via implicit values, implicit arguments. And then because other languages have actual first-class support for Haskell, or for type classes like Haskell and Idris, we use the implicits and kind of mimic what a type class is in Scala. So this is the structure of a type class. This is sort of your like recipe. So safe to serialize is the type class. It's just this trait without any sort of any implementation whatsoever. It's just like an interface or a contract. And then we say that when we implement an instance of the type class for a type, so we come up with this type argle-bargle, and we create an instance of this type, and we put on an implicit. Now we basically have your instance of the type class of safe deserializer. It doesn't have to be a val. It can be some object or class or whatever. Just so long as you have this implicit argument that allows you to resolve an instance of this type class of A. Let's see. So and then what's also nice with type classes is that, like we showed before, if you create some type and then you try to deserialize it, but you don't have a deserializer for that type, you get a compile time error. And all you need to do is provide an instance of that type class for that type, and then it compiles. One of the really neat things from Scala that you don't get in Haskell is that in Haskell, type classes are global. We actually get some kind of hairy and complicated scoping, but we get to have multiple instances of a type class for a given type. So in this case, I've actually made a test instance of a deserializer for address that's special just for this scope. So our safer deserialize address will correctly do the address using the safer deserializer. If I use the test deserializer, I get back none because that's my implementation and test. So that's nice. Further, one of the neat parts in Scala as well is you can basically get this inline syntax as well that gives you more of like an OO quality where this as method can be defined. So you can take any type class, any sort of property, and apply it using the syntax, and now get inline syntax for your deserializer. So type classes are really great, but as you saw, there's a lot of boilerplate. One of the libraries out there that is really nice is Simulacrum, which gives you more of a first-class support for type classes. You can use this annotation, and it basically generates all of that extra code and operations and things so that you can, this compiles as well using Simulacrum. Other things with type classes to remember. Type classes generally, you want them to be lawful. And so that when other people create instances of your type class, that they know that their instance works. So there's a set of libraries called Discipline and Scala check that allow you to enforce or give the user of your library the ability to test their instance of the type class to make sure that it follows your laws. And you can compose them and share these laws. It's really nice. So that's another added benefit. So here's a non-exhaustive list of places where type classes make sense or can be used. From method overloading to replace generic interfaces for generating data. We talked about serialization. Anytime you see those big match blocks with tons of types that look like that mapping function where you're basically dynamically dispatching to a similar behavior, that's another case where you might be able to do that. And so, as Rob Norris said, in my experience, I've never regretted replacing a superclass with a type class. I, on the other hand, have regretted that. So I have an example of exactly where that didn't go so well. But first, let's talk about operator overloading. This is sort of how you might do subclassing or wrapping classes. If you wanted to add functionality to something like string or int, you might create this wrapper class. And so if you're like doing business and you want to do business on a string or you want to do business on an int, you write these classes and then you pass in some superclass that you can call that on. And then if you need to override it again and do like serious business on a string, then you can, this is all fairly familiar from the OO paradigm. You can flip that and do that with type classes. So with type classes, you create your trait again, your instances for these types, and then now, and this like nice little apply syntax thing makes it makes the syntax nice in Scala. So, and you can still have your serious business, in a different area than your normal business. And so, using the inheritance method of overloading, you can call it that way, or you can use this nice typed inference from business can see that hello is a string, so it pulls out the string instance of the business type class and then prints that out. Or if you need to do real serious business, you can do that, and it knows that it can find the double version of the business and print that out. And that all happens at compile time. Again, compile time is really good. Now, let's take a look at where type classes don't fit so well. Instances, so like inheritance, for example, if you know if you control all of the objects or the types that you're using, and it's a small discrete amount, type classes are a little too heavy-handed, I think. You should just use regular inheritance. If you can't express a law in your type class, it's probably not a type class. Again, this is just another example of like, if you had an interface, it makes a lot more sense than sort of this because you only have your domain objects.
I hate to rush, but we got to get ready for the next session here.
I have 18. Oh, okay. All right. I guess because I started late.
Yeah,
all right.
Sorry.
Okay. So we're totally done?
Yeah, unfortunately.
Okay.
Sorry.
Slides online that you can watch.
Yeah, I'll put these slides online. Unfortunately, it started like 5 minutes late, so I didn't get to finish. Okay.
All right. Sorry about that.
All right.
Thanks a lot.
Thanks.